Hi there. All right, so today we're going to look at systems of linear equations, and ideally, this is a nice little review for you. You have seen this actually probably clear back to Algebra 1, but we're just going to hit the high points on it and actually get into some more complex things like the three variable systems. Now, that's a different deal than Algebra 1, so let's get started. All right, so we're going to get started with just the two variable systems, and there's three cases for what might happen when you're solving a system of linear equations with two variables. You might end up with, and remember that when you're doing those two variables, those are really just lines, and you're looking ultimately at where the lines intersect, and that would be this scenario right here. This is probably the most common scenario. You got two lines, they intersect. This spot right here where they're intersecting is the solution to the system. Remember that a system is two equations in two variables, and this ordered pair would be the x and y that would actually solve both of the equations that you're given. All right, this is the fancy term that we use. We say that it is consistent because it does have a solution, but that they are independent of one another. It's just two random lines. All right, so that's the most common. But these other two can also happen, but they're a little less likely to happen because they're so special. So this one right here in the middle, we're looking at that one, and in that scenario, we have, it looks like there's just one line, but really it's one line graphed on top of itself. So there are two lines. It'd be two equations that would be identical to one another, though oftentimes they kind of hide that they are identical by rearranging them and maybe multiplying them all by something to build them up so you don't notice it so much. But in the end, they're the same equation. All right, again, you're looking for where they intersect. Well, when you have one line on top of another line, they're intersecting everywhere. So since there's still going to be a solution, we still call it consistent. They are dependent that they end up having to be the same line. All right, in a situation like this, we would say that we have infinitely many. I'm just going to write infinitely many solutions, because anywhere on that line would be an ordered pair that would work in both of the two equations you have. All right, and then the third scenario would be this two lines and they end up being parallel. Again, kind of a rare situation, very specific, but when you look at where they intersect, well, they don't. So we consider that an inconsistent system, meaning there is no solution for that. So we would write no solution if that happened. All right, now we do have three ways to solve a system, and the first way is just to graph it. Now I like that so you can kind of get a visual of what's happening and you can see why the answer is what it is. However, it's kind of time consuming, and you're really dependent on that point where they intersect happens to hit a nice grid line nicely. And so it's not maybe the most efficient or most accurate way. So then we have two other ways that you're probably more familiar with. We have elimination, where you're stacking the two equations and you're trying to get one of the variables to eliminate by adding or subtracting the equations together. And then the third version or option is substitution. And that's when you have a variable isolated and you can substitute into the other equation. It's really just another way to eliminate one of the variables. Depending on how long ago Algebra 2 was for you, we'll go ahead and kind of go through some of the things on each one of these. So for substitution, works well when you have a variable that has a coefficient of 1. Or maybe if both equations were solved for the same variable, like they're both a y equals blah, 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 something like that. But you kind of want that variable to be either isolated or have a coefficient of 1. So what you're going to do is you're going to solve for that variable. Once you have that variable isolated, then you'll plug it into the other equation. And then you solve for the remaining variable. Remember, you're going to have two variables on this. So when you look at this system that I have right here, two equations, they each have an x and a y in it. And what I'm trying to identify is the variable that has the coefficient of a 1. And that would be this one right here. Sometimes there's more than one variable that would work, but in this case, there's just this one right here. So what I want to do is I want to solve for that variable or isolate it. So that means getting rid of this 3y. So I'm going to take that 3y to the other side. So I'm going to end up with a 5 minus 3y. And then since x is actually equal to this 5 minus 3y, I'm going to grab that 5 minus 3y and I'm going to plug it in for the x in the other equation, since that's what x equals. And then I would rewrite this. So this would end up being a -2. And instead of your x, you're going to put in a 5 minus 3y. Minus 4y equals -5. And then you should notice that, oh, I only have y's left in this equation. That's going to be ideal. I'm just going to solve for y. So let's distribute. Combine like terms, get your y's on one side and your numbers on the other. So you're going to have a 2y when you combine those like terms. And then I'm going to add a 10 to the other side. And so I end up with a y equals 5/2 or 2.5. Be sure to pay attention to what the directions say as far as what they want you to round to. So then what we do, well, so we've solved for the y here. That's what this step 3 is, solve for the remaining variable. But really, we've got to take that y and we're going to plug it in. And this is one of the things that's really nice about substitution is that you already have this variable here isolated. So the plugging back in works really nice. So x is equal to 5 minus 3. And then I put in that 2.5 for the y. And then I'm just going to math that out. So 3 times 2.5 would be 7.5. So I'm left with a 5 minus 7.5, which is a -2.5. Now remember that your answer is really the ordered pair where these two lines would intersect. And so you always write your answer as an x, comma, y. So -2.5, comma, 2.5, x, comma, y. That would be the ordered pair that would work to solve both of these equations. It's the only ordered pair that would work in both. It's also the point where these two lines would intersect if I graphed them. Okay, that's substitution. All right, let's take a look at elimination. This is a second option, probably my favorite of all the options. And eliminations works really well when both equations are in standard form. Standard form is the x plus the y equals, oops, I guess the form's already there. Okay, so x plus the y equals the number. So here's your goal when you're doing elimination. You really want one of the variables to eliminate, and you're really just combining them together. And so it really works ideal if you have one that's that have the same coefficients, but one's positive and one's negative. Now, sometimes you'll get lucky with that, but it's not Algebra 1 anymore, so don't count on it. But it says multiply one or both of the equations to make a set of coefficients be the same number with opposite sign, because we want them to cancel out. And then you're going to combine the equations. I don't like to use the word add or subtract, but ultimately that's what you're doing. But I don't want to get caught up with, am I adding a negative or am I subtracting the negative? I'm just going to combine them. All right, once you have them combined and you've gotten one of those variables solved for, then you just solve for the remaining variable. So you'll plug it back in to see what the other variable is. That doesn't work out quite as slick as in substitution, but we'll work through it. All right, so we're going to play a little Algebra 1 to start with, and I'm going to be nice, and I'm going to give you these two terms right here you can see are the same, but one has a +8 and one is a -8. That's an ideal scenario because when I combine them together, it's just going to go away. And so I'll probably just slash it and then combine here. That's going to get me a 3x equals, and then 20 and a negative 8 is a 12. So x is 4. Once I have that, then I plug it back in. Now, neither of these is really isolated nicely for plugging back in. So you're just going to have to kind of pick one of them and just work through it. I'm going to grab, I think, this 4, and I'm going to plug it in right there. So that's going to turn into a 5 times 4. So that's a 20 minus 8y equals 20. Subtract the 20. Oh, this is going to work out nice. And then divide by the negative 8. So you end up with a 0. So your ordered pair, your solution, your x comma y is 4, 0. All right. All right, let's step it up a little bit. Let's do something that's not quite as perfect. This next one here. In fact, the bottom one is in a nice standard form, but this one isn't. And I need like terms to line up, and they so obviously do not here. So I'm going to rearrange this equation. I'm going to add this 2x over here so that it'll be a 2x plus 7y, and then it'll line up a little nicer. So I'm going to do a 2x plus 7y equals 4, and then a 3x plus 5y equals negative 5. Okay, so that's a little nicer, but again, nothing is going to cancel super great. So I have to decide, would I rather get these to be the same? I could make them both be 6s, or I could make these both be 35. I feel like 6 keeps my numbers a little smaller. So that means I'm going to take the top equation times 3, so that'll turn that to a 6. And then this one I'm going to take times a negative 2, so that'll be a negative 6. Sometimes it's good as far as trying to troubleshoot later, maybe to show a little bit of work of what was your strategy here. That's what I'm going with. Okay, so then what I end up with for my new system is going to be a 6x plus 21y equals 12. And then when I distribute the negative 2, I'll have a negative 6x, negative 10y, and a positive 10. Now I'm going to combine, which means those go away. 21 minus 10 is 11y. And combine a 12 and a 10, that's a 22. How nice is that? Y is going to equal 2. Then I'm going to plug that back in somewhere. I can plug it into the top equation or the bottom. I'm going to grab it, and I'm going to go the long way around here. I'm going to put it right there. So then I'm going to have a 7 times 2. So that's a 14y, or sorry, not 14y, just 14 equals 4 minus 2x. Subtract the 4, divide by negative 2. All right, so my ordered pair here, my solution is a negative 5, 2. Remember, you always put it as an x comma y, regardless of which one you found first. Okay, there you go. There's your quickie review of elimination. Let's talk through those special situations that can happen. Now, we already know what's going to happen graphically, but if I'm not going to use graphing necessarily as my main method of solving, how do I know that parallel lines happened or that they ended up being the same line? How do you tell? Okay, so let's solve them algebraically and see what that would look like. All right, so on this first one, I'm going to rearrange that so that top equation is going to be like in standard form. So it's going to be a negative x, and I'm going to add the y over equals negative 2. This one here, 2x minus 2y equals 0. And then I think I'm going to work on my x's, and I'm going to take everything in the top equation times a 2. And that'll make that be a negative 2x. And then with my positive 2x, that'll play out nice. So next set of equations would look like this. Don't forget, one of the reasons I like to do these parentheses is because oftentimes people will distribute this 2 through these and then forget to do their constant. And so there's something about putting parentheses in there that forces me to go all the way to the end a little bit better. Okay, then you have a 2x minus 2y equals 0. And look at what happens here. Yes, the 2x's cancel out. Oh, I'm sorry. I was talking there and I goofed up. That 2 times y should be positive right there. My bad. So what happens then is that these cancel as well. And if everything cancels, all you have left is a 0. Equals, over here I have a -4. All right, so right here, this is false. 0 does not equal -4. And if you get a false statement like that, that's going to be a no solution scenario. That means those lines were parallel. But that's what it looks like algebraically. Both your x and your y cancel out like that. All right, let's try something a little bit different over here on the right. The top equation, already in standard form. This one is not, so I'm going to bring the 3y over. Want to get one of the variables to eliminate. I think I'm going to work on my y's because the numbers are a little bit smaller. So that just means taking the top equation times a -3. So my new equation is a -12x minus 3y equals -18. The bottom equation I'm not going to mess with. You can probably already see what's going to play out here. Yes, the 12x's cancel and the 3y's cancel. Again, both the x and the y disappear. But look at what's different on this one. When everything disappeared, I put a 0, but on the right side, it also equals 0. That happens to be a true statement. If what you end up with is a true statement, then that's or not all solutions, but infinite solutions. That means the two lines landed on top of each other, but they kind of hid that. And you would, when you first glance at these two equations, you're probably not going to notice those are really the same line, the same equation. Okie doke. There you go. There's your special situation. Okay, let's look at where we could use these systems of equations to solve some sort of a scenario. I liked this question because it's quite a bit different than probably any of these that you have seen before. So I'm going to highlight some, there's a lot of words in here, and that's okay. I'm just going to highlight maybe some of the key information that we're going to need. So it says here that the salaries for the same position can vary depending on the location. Okay, that's true. So in 2019, the average salaries for an accountant in San Diego and Salt Lake City was $53,000. So the average salary between those two cities was 53,000. Okay, that's going to be one of my equations right there. And then it comes back and it says the median salary in San Diego, though, exceeded that salary in Salt Lake City by $6,733. So San Diego exceeded Salt Lake City by $6,733. Determine the median salary for the accountant one position in the two cities. Okay, here we go. Not one that we've probably done before like this. So let's talk about the average of the median salaries. That seemed a little bit redundant, but the average is the mean. So think about how you would find the average or the mean of these two salaries. Well, you would just add them and divide by how many there are. And in this case, there's just the two cities. So let's designate San Diego as the X, and I'm going to designate Salt Lake City then as the Y. So to find the average, I would take Salt Lake City's salary, add to it, did I say that right? San Diego plus Salt Lake City, divide it by 2, and it should equal that average, that 53,763.50. Boy, they couldn't give me a nice number there. All right. This is just an equation. It happens to have two variables. The only way I can solve it is if I have another equation with those two variables. And then that means here, the next part's going to give me my other one. San Diego, which is X, exceeded the median salary of Salt Lake City by this 6733. Now you could write this a couple different ways, but in my mind, what that says then is that X is going to be bigger than Y because San Diego was higher than what Salt Lake City was. So if I want to write an equation to show some sort of equality here, I would have to take San Diego's salary. And since it's bigger, I would have to subtract the 6733, and then that would be the same as whatever it was in Salt Lake City. Another option, you might have chosen to add the 6733 to the Y. Take Salt Lake City's and add 6733 to build it up to what San Diego is. Either one would be fine. I'm going to rearrange it probably anyway. Okie doke. So looking at this, I really like that this Y is isolated right now. I feel like that sets it up nicely to do substitution. I'm going to grab this guy right here, and I'm going to plug that in for the Y right here. But I think I'm also going to try to get rid of this fraction. So I'm going to do two steps in one here. I'm going to take both sides times 2, which is going to make this a lot bigger, but it's going to get rid of this fraction. At the same time, I'm going to do my substitution. I'm going to plug that in. So here's where I'm going to be then. I'm going to have an X plus, and instead of the Y, I'm going to put in this X minus 6733. Since I'm adding, those parentheses that I just put there are totally optional. All right, the other thing I'm going to do is go ahead and take both sides times 2 at the same time here. So that's going to equal, grab my calculator here. Instead of the 53,000, I'm going to have the 53,763.5, and I'm going to double it. Okay, it's going to make my numbers a little bit nicer. 107,527. Okay, like I said, I have gotten rid of the Y in this, and so these parentheses, totally optional. I'm really just going to combine like terms. I have an X plus another X, that's a 2X. But this 6733, I'm going to move over to the other side. So I'm going to, actually, I'm going to add that 6733. Divide by 2. And what I have here is the X. And remember that X is the San Diego salary. So I'm going to put a dollar sign on that, and I'm going to say, I'm going to abbreviate San Diego. San Diego median salary. Oops, missed my R. Okay, then all I have to do is grab, remember substitution is great for that last part of substituting in because this is already isolated. So I'm going to take this and put it in right here, and then I'll have my Y figured out. So the 57,130, and then subtract the 6733. I got 50,397. And that's the Salt Lake City median salary. Put a dollar sign on that. Remember, we did say that San Diego had a higher salary, and my work does show that it does have a higher salary. Okay, so there's just a place where we can kind of set up two equations that have the same variables. Now we're going to move on to something harder here that you would have seen in Algebra 2, but certainly not in Algebra 1, and that's solving a system of 3 variables. So now you're not just going to have an X and a Y, you're going to have an X, a Y, and a Z. Now, the only way you can solve a system of 3 variables is if you have 3 equations. So now there's going to be a little bit more involved. This picture, I kind of like it because it shows some of the different things that can happen. Because when you're solving this system of 3 variables, we're no longer talking about lines and where they intersect. It becomes a 3-dimensional thing. And so we are looking at a plane and how planes intersect. And so now you're looking at an X, a Y, and a Z. So if you think of your graph, you have horizontal, you have vertical, but also you have depth in this that kind of creates 3 dimensions. So you can see in the diagram, I don't need to read through it, but you can see all the things that might happen in this scenario of what you might have for where these planes intersect. Here's kind of a brief to-do list. So you have 3 variables, 3 equations. What you're going to do is you're going to pick 2 of the equations, and you are going to eliminate one of the variables. Then you pick 2 different equations. So you have 3, so maybe you picked A and B equation, and now you might do A and C or B and C or something. Pick a different set, but you have to eliminate this same variable. So if you got rid of the Z, then you got to get rid of the Z the second time, which means you're going to end up with 2 equations that have only 2 variables left. So using those 2 equations from step 1 there, you're going to eliminate another variable. And ultimately what you're doing is you're going to solve the system of 2 variables. And once you've solved the system of 2 variables, let's say you now know what X and Y are, you can use that X and Y to plug into the original, so then you could figure out your Z as well. So that's what you're shooting for here, is to get an X, Y, Z. It's called an ordered triple instead of an ordered pair. Now, there's not necessarily just one way to do these. There might sometimes be a better way or an easier way, sometimes not. It just maybe sometimes is what grabs you. So when I'm looking at this problem, I guess what grabs me is that this Y right here does not have a coefficient on it. So it's going to make it easy to group with other equations. So here's what I'm going to do. Now, I know that some teachers like to label these like it's an A equation and a B equation and a C equation. You can do that if you want. Really, what I want is organized work. I don't have to necessarily see that, but let's group these and show nice work. Typically, what I would do is I'm going to grab, again, I'm going to use that B equation twice because I like that Y. So I'm going to use these 2. And if I use A and B, I guess this is, I don't know how many, if this is our only slide. Okay, here's what I'm going to do. I'm going to erase what I have there. I'm not going to write the A and the B. What I am going to do, though, is I'm going to go ahead and group these 2 together, and I'm going to have to take this equation times a 2, because that's going to turn it into a -2, and that will make the Y eliminate. So the top equation stays put. No changes to that. The second equation is going to become a 4x minus 2y plus 6z equals 8. Sometimes you have to multiply both equations. I'm getting lucky here. 2 y's drop. I have a 7x plus 10z equals 9. Okay, if you like to letter your equations, that new equation would be probably equation D. Or I don't know, 1, 2, 3, and this is 4, whatever you want to do. All right, so now I pick another 2 equations. I'm going to pick these 2. Again, I like that y. And so that means I'm going to take the bottom equation times a -3. So I'm sorry, no, I'm not. I'm going to take the second equation, not the bottom equation, times a -3. So I'm going back to the original and take that whole thing times -3. That's going to be a -6x, positive 3y, -9z equals -12. And I'm grouping it with the bottom equation. Remember that I have to get rid of the same variable twice. So I'm getting rid of the y again. And now I have a -x minus 4z equals -13. And I have 2 equations now that have an x and a z in them. That was my goal, to get it down to where I have eliminated the same variable in those two. Now I'm going to solve this system. Now I'm going to go ahead and stick with elimination here. So I'm going to stack these. But as I stack them, I feel like I might want to go ahead and save myself a step. And I guess I'm going to eliminate the x. So I'm going to take this one times 7 as I rewrite it. All right, so then I have a 7x plus 10z equals 9. And then I'm going to take the other equation, and I'm going to end up with a negative 6x, and then a minus 28z equals, and 7 times negative 13 would be a negative 91. When we combine, 7x's are going to drop. I get a negative 18z equals, and that'd be a negative 72. And that actually will divide nicely. 18 will go in there 4 times. So what we got is z. We now know what z is. Then we start back substituting, and you can substitute this back into either this version, or you can put it into this version. You could put it into the version that we multiplied by 7. That wouldn't be as pretty. I think I'm going to take the 4, and I feel like it's going to, this looks like the simplest version, so I'm going to put it there before I did the times 7. So I'm going to take negative x, put 4 in for z, so that's going to be a minus 16 equals negative 13. Add the 16 over, so x is equal to negative 3. And so now that I know x and I know z, I'm going to take them and plug them into any one of these 3 at the beginning. I kind of like this one, I suppose. It looks like it has the smaller numbers. So I'm going to put negative 3 in right here, put 4 in right here, and I'm going to go solve for that z. So let's see what that's going to look like. 2 times, and instead of x, it's 2 times negative 3, so that's a negative 6. Minus y, that's what I'm looking for, plus 3 times z, so that'd be plus 12, equals 4. All right, so I'm going to go ahead and combine, in my head at least, negative 6 and 12, that's a 6. I'm going to subtract 6 to the other side. So then I have negative y equals, subtracting a 6 is going to be a negative 2. So y would equal a positive 2. You have your x, y, and z. You want to be sure that you answer it as an ordered triple. It would look like a negative 3, comma 2, comma 4. X, y, z. Final answer. Now, ultimately what this means is these 3 numbers right here, if I plug them in to this equation or into this equation or into this equation, all 3 of those would work. All right, last one. This again, maybe something a little bit different than what you've done before with solving application kind of problems. So it's using the idea that given some data, it has a known quadratic relationship. And so this is what our quadratic is going to look like. We're going to use this form right here. Now, the problem is that I don't know what A, B, and C are. And that's what my goal is. I'm going to figure out what A, B, and C equal. And to do that, I have to have 3 equations to figure it out. So what I really have is some data over here. And so the average number of hours of sleep compared to the death rate. And so it looks like, just in general, as you look at it, the less sleep you get, the more likely you're going to die, I guess. I don't know. Actually, that's not true. Let me back this up. Okay. Actually, what you should see is that right here, 4 hours, not near enough sleep. 7 hours is pretty good, I guess. But then if you start sleeping too much, look at what happens to the death rate. Okay, so it sort of starts to turn around. So really what you have here is sort of like this ideal amount of sleep. And if you sleep less, it's not good. If you sleep too much, it's not good. And so what we're going to do is come up with this model so then we can predict, I guess, given the number hours of sleep, what that death rate per year would be for those people. Okay, so here we go. I have a bunch of X's and Y's is what I have here. So I'm going to write 3 equations, and put in that X and that Y for it. So the first one, I'm going to use my model and I'm going to put in a 1682 for the Y equals, I don't know A, but it's going to be times 4 squared. Actually, let me clean that up and save myself some work. It's actually going to equal A times 4 squared. So I'm going to write that as a 16A. And then plus, don't know B, but again, I'm putting in the X. So that's going to be 4B. And then I don't know C. That's the idea right there. So why don't you do the next two equations on your own and then come back to me. Okay, I forgot to tell you to pause the video. Hopefully you did, but here we are. Okay, this is what we've got. So I am going to put you to work on your own to sort of hurry this up a little bit today. So the next step, just like last time, we are going to group. We're going to pick two and then pick a different two. Now, I look at this like the C's are the obvious thing to be eliminating here. So I'm going to do the same thing I did last time. I'm going to group these two together, and then I'm going to group these two together. And in both scenarios, I'm going to need one of those C's to be negative. So here's what I'm going to do. I'm going to sneak in. I'm just going to kind of make it official here. I'm going to go ahead and change all the signs. So I'm taking this middle equation times a -1. So I'm going to change these all to negatives. And that way, when I group it, that C will cancel. So let's group these two first of all, and I don't even have to like multiply anything other than that -1. And then I'm going to group these two together. So what I would like to see from you is your two equations that you have after you've eliminated the C in both sets. Okay, pause the video, go do that, and then come back. All right, here are my two equations. You check yours, make sure we are in agreement on that. And now what we're going to do is decide whether we want to get rid of the A's or the B's. All right, I'm looking at it. What are you thinking? Which one looks easier to get rid of? I hope you're thinking B. All right, I think there's a big difference there. So I'm going to take this equation times 2. That's going to make that be a -6b. I'm going to take this equation times 3, and it'll be a +6b. So again, let's go ahead and take a minute, pause the video, get your calculator out and do the math, and let's eliminate this down to a single variable. All right, take a look. I got a 104.5. Seems like a weird number. It's okay. It was real life data there, so it's not going to be pretty numbers. If you agree, let's keep moving. If you don't, just pause the video and check it out. All right, so then my last step is I'm going to take the A, I'm going to plug it into one of these two equations, probably this one here, I guess. Numbers are smaller. Put it in here, solve for the B. Once I know B, plug it into one of these to figure out the C. Okay, you go do that. All right, here's my A, B, and C. Crazy as it is, I even double checked it myself. It actually does work in all three equations. So now what's different here is we don't answer this as an ordered triple. Our goal is to find the quadratic equation that models it. So I'm going to take this A, B, and C and plug it back into the model. So my final answer, I sort of ran out of room, so I'm going to go up here next to the table and I'm going to write Y equals, and instead of an A, I'm going to put in my 104.5 x squared. And then my B value, so then it's a minus 1501.5 x, and then plus 6016. And that's how we'll write our answer. Okay, so that's a little trickier than some of the other stuff. Okay, but that does wrap it up for us today. I know most of that's review, but it's also a lot in one day. So go give your homework a shot. Good luck.